Imagine 10,000 multi-million-dollar processors drawing enough electricity to power a small city.
Like a massive amount of power.
Yeah, and all of it hanging entirely on a single microsecond of latency.
Just 1 microsecond.
Exactly. One delayed signal, one dropped packet across miles of fiber optic cable, and the entire system just grinds to a halt.
It's kind of terrifying when you think about it.
It really is. And, well, it's late. Maybe you're coding, maybe you're just unwinding after a brutal deployment, but wherever you are, welcome to the deep dive.
The lights are low, the screens are glowing.
You got it. And today, we are exploring the chaotic, bleeding edge of AI infrastructure.
Oh, this is a fun one.
It is. Our mission today is to understand the sheer mind-boggling scale of distributed AI training. We're pulling from a technical module focused entirely on how engineers actually run a single model across thousands of GPUs.
Because, we have to start with a fundamental physical reality here.
Right. Frontier models have just gotten massive.
Physically and mathematically massive.
Yeah, they have grown so large that they completely eclipse the capacity of any single piece of hardware on the planet. Like, the days of training a state-of-the-art model on a single rig humming quietly under your desk.
Oh, those days are completely over.
Completely. You physically cannot fit the baseline state of a frontier model into the memory of the most expensive single GPU on the market today.
What's fascinating here is that this completely shifts the paradigm of what it means to write software.
Oh, absolutely. How so? Exactly.
Well, if you're building a standard web application, your primary constraint is usually the logical complexity of the code.
Sure, like, are your loops efficient? Is your database index? That sort of thing.
Right. But at the frontier of AI, the code itself, the actual Python or CUDA script, is almost the easy part.
Really? The easy part?
Yeah, relatively speaking. Because we aren't just talking about writing good code anymore. We are talking about orchestrating a massive distributed symphony of hardware. You're taking tens of thousands of individual processors and trying to force them to function as one single unified brain.
Which just sounds mathematically impossible.
It's definitely an insane challenge. The engineering challenge transitions from purely algorithmic complexity to, distributed systems complexity.
Yeah.
On a scale that human beings have, frankly, never attempted before.
Right, because if this frontier model is just fundamentally too big to fit onto one graphics card, the absolute natural first step, the immediate instinct for any software engineer is to figure out how to divide the workload.
Exactly. Divide and conquer.
Yeah, like if the database is too big, you shard it. If the rock is too heavy, you get more people to lift it.
A very human approach.
True. And the notes we have lay out two primary complementary strategies for dividing this compute. Data parallelism and tensor parallelism.
Yes, the two heavy hitters.
Okay, let's unpack this with an analogy because the way these two interact is just brilliant.
I love a good analogy. Go for it.
So imagine you are running a massive high-end restaurant. Data parallelism is like having a massive kitchen where 50 different chefs all have the exact same recipe.
Okay, so the recipe is the exact same model.
Exactly. But they are cooking completely different customer orders.
Huh? I see.
They are processing different batches of data simultaneously to get through the evening rush faster. So Chef A is cooking table 1's order, Chef B is cooking table 2's order.
That's a really great baseline. Data parallelism solves the problem of throughput.
Right.
Like, you have trillions of tokens of text to process. You need to churn through the internet faster.
Exactly. But tensor parallelism is a totally different beast.
Oh, yeah, it is.
Because if the recipe itself is just too massive and complex for one chef to physically handle, say, it requires lifting a 400-pound side of beef. Data parallelism doesn't help at all.
No, it really doesn't.
Having 50 chefs each try to lift their own 400-pound beef still fails. Everyone's just straining and dropping it.
It's a disaster in the kitchen.
Right. So tensor parallelism is like having two chefs grab that exact same side of beef and slice it perfectly in half at the exact same millisecond so it fits into the pan.
That is a highly coordinated kitchen.
Yeah. They are splitting the actual neural network layers, the actual matrix multiplications, across multiple GPUs simultaneously.
The math itself is divided.
Yes, computed in parallel, and then the results are instantly synchronized.
And that synchronization is the key. It perfectly illustrates why engineers building these systems don't choose between data parallelism or tensor parallelism.
Wait, they don't choose. They use both.
They deploy both simultaneously, always.
Oh, wow. Okay.
Yeah, so tensor parallelism solves the depth and weight of the computation, allowing the physical execution of matrix math that is just, too large for one chip.
Right, the heavy lifting.
Exactly. But once you use tensor parallelism to spread one replica of the model across, say, 8 GPUs in a single server node, you still need throughput.
Because you still have to read the whole internet.
Right. So you take that 8 GPU cluster, clone it thousands of times using data parallelism, and feed different chunks of the internet into each cloned cluster.
So you are scaling both the depth of the computation and the width of the data pipeline at the exact same time.
Precisely.
But looking at this architecture, there is a massive inefficiency that jumps out immediately, like a huge flaw.
Oh. What do you see?
Well, if we use data parallelism, where we have thousands of clone clusters, and each cluster holds a full replica of the model's parameters and mathematical states, aren't we just wasting a catastrophic amount of memory?
You are definitely hitting on the core problem.
Right, because we're redundantly storing the exact same gigabytes of data thousands of times over.
Thousands of copies of the exact same weights.
Yeah. For any engineer trying to optimize memory allocation, duplicating terabytes of identical state across a data center sounds like an absolute nightmare.
It is a nightmare. And it was the primary wall that AI researchers kept hitting for years.
I can imagine.
Let's look at the actual numbers to understand why. A single high-end GPU today might have, say, 80 gigabytes of memory.
Okay, 80 gigs.
A 70 billion parameter model, just storing the weights at 16-bit precision, takes up about 140 gigabytes.
Wow, so the model itself literally doesn't even fit on one GPU.
Not even close. But that's just the resting state. During training, it is so much worse.
Wait, really? How much worse?
This leads directly into the advanced sharding techniques we need to cover, specifically systems known as FSDP, fully sharded data parallel, and zero.
Zero, like the number zero.
Yeah, it stands for the Zero Redundancy Optimizer.
I love how literal the naming conventions are in this field. Zero Redundancy Optimizer. It does exactly what it says on the tin.
It really does. It fundamentally rethinks how memory is allocated across a massive cluster.
Okay, how?
Instead of redundantly copying the model state across every single data parallel rank, Zero eliminates that waste by slicing up the essential components of the training state and scattering them across the GPUs.
So it's basically sharding the memory.
Exactly.
Yeah.
Specifically, they shard 3 things: the model parameters, the gradients, and the optimizer states.
Okay, so parameters and gradients, most engineers know what those are, but the optimizer states.
The optimizer states are the real culprit here. They take up a huge amount of space.
Right, because the optimizer, usually something like Atom, right, is tracking the historical momentum of how those parameters are changing.
Yes. Think about what the Atom optimizer actually does. For every single parameter in a 70 billion parameter model, Atom stores a 32-bit float for the momentum.
Okay.
And another 32-bit float for the variance.
Oh, wow.
Yeah, that's 8 bytes of memory per parameter, just for the optimizer state.
Just remember how fast it's learning.
Exactly. Add in the 32-bit copies of the gradients and the weights, and suddenly the optimizer state is taking up 3 to 4 times more memory than the actual model itself.
That is insane. It's a massive multi-terabyte footprint.
It is. So by taking those parameters, gradients, and these bloated optimizer states and slicing them into thousands of tiny shards, FSDP and Zero ensure that each GPU only holds a tiny fraction of the total state.
They dramatically reduce the memory requirement per individual GPU.
Exactly. It's an elegant solution.
Okay, but I'm looking at this architecture, and my system's design brain is flashing red right now.
Uh-oh. What's the catch?
I feel like I need to push back on this on behalf of every SWE listening right now. Wait, if FSDP and Zero slice up the parameters, gradients, and optimizer states, doesn't that mean no single GPU actually possesses the full picture of the model at any given time?
Yes.
If a GPU only holds 1,000th of the weights, how can it possibly compute the forward pass for an entire sentence of text? Aren't we just trading a memory bottleneck for an apocalyptic network traffic jam?
This raises an important question, and your system's design brain is absolutely right to be flashing red.
Thank you. It just seems crazy.
You've identified the core trade-off of modern AI scaling. You are entirely correct. No single GPU has the whole model. They are effectively flying blind.
So how do they do the math?
Because they don't have the whole picture, they have to constantly ask each other for the missing pieces.
Constantly?
Yes. Right at the exact microsecond, a GPU needs a specific parameter to calculate a matrix multiplication, it reaches out across the network.
Okay.
It grabs the missing shards from its neighboring GPUs, stitches them together, computes the math, and then, this is the crucial part, it immediately deletes those shards from its local memory.
Wow. Wait, really? They assemble a recipe, chop the onion, and then instantly burn the recipe so they have room on the counter for the next instruction.
That is a perfect way to put it. It is highly aggressive, just-in-time memory management.
That sounds exhausting.
The shards are fetched, used, and discarded in milliseconds.
But, as we kind of pointed out, when you solve a memory bottleneck by forcing 10,000 components to constantly request massive chunks of data from each other, you don't actually eliminate the bottleneck. You just move it somewhere else.
You move it to the network.
Exactly.
Yeah.
Because if these GPUs are constantly, frantically asking each other for missing pieces, the speed at which they talk to each other becomes the whole ballgame.
Yep.
If the network is slow, if there's even a fraction of a millisecond of latency, the GPU just sits there waiting for the data to arrive.
And this brings us to the heartbeat of distributed training.
Okay, let's get into it.
We are looking at specific communication operations that dictate this massive data flow, primarily two operations named all gather and all reduce.
Here's where it gets really interesting for the infrastructure nerds out there.
Oh, absolutely.
Because if the GPUs are the compute engines, like the actual muscle doing the heavy lifting, then the interconnects, the cables and switches wiring them together are essentially a high-speed nervous system.
A very fragile, very expensive nervous system.
Right. If you try to run this level of communication over a standard TCP/IP network, it's an absolute disaster.
Total failure.
Without specialized interconnects, these multi-million-dollar GPUs would just be incredibly fast calculators sitting idle in traffic.
Stuck on the digital highway.
Yeah, they'd compute their piece of the puzzle in a microsecond and then wait 10 milliseconds for the data packets to arrive over standard Ethernet.
And that idle time is the ultimate enemy of distributed training.
So how do all gather and all reduce fix this?
Let's break down those operations. All gather is the process we just discussed. Every GPU broadcasting its specific shards so everyone can temporarily assemble the full model to do a forward pass.
Okay, got it. Gather the pieces.
Right. And all reduce is the reverse.
Reducing it back down.
Yes. After the backward pass is computed, every GPU has a tiny piece of the updated learning, the piece of the gradient, and they have to synthesize all those scattered updates into one unified mathematical truth across thousands of chips simultaneously. To do this without stalling the compute, you cannot rely on standard networking protocols.
Because standard networking protocols have to go through the CPU, right?
Precisely the issue.
The CPU is just too slow.
Way too slow. In a standard network, a data packet arrives at the network interface card, the NIC. It triggers a hardware interrupt.
Which pauses everything.
Exactly. The CPU has to pause, copy that data from kernel space into user space, and then route it to the GPU. That operating system overhead takes microseconds.
And a microsecond doesn't sound like a lot, but...
In AI training, a microsecond delay, multiplied by billions of parameters, multiplied by trillions of operations, compounds into months of wasted training time.
Months?
Yes. This is why the sources emphasize technologies like NVLink and InfiniBand, which utilize RDMA.
RDMA, Remote Direct Memory Access.
Yes. RDMA allows a NIC to write data directly into the memory of a GPU across the data center, completely bypassing the CPU and the operating system kernel.
So they just skip the middleman entirely.
Completely. NVLink handles this for GPUs sitting right next to each other in the same physical server box, allowing them to share memory at staggering bandwidths.
And InfiniBand?
InfiniBand is the network that connects the thousands of different servers across the massive warehouse. InfiniBand actually allows a GPU in rack A to read and write directly to the memory of a GPU in rack Z, with almost zero CPU involvement.
Direct memory access across a warehouse. It's like telepathy for silicon.
That's a great way to put it, telepathy.
So you have these high-speed InfiniBand networks firing data back and forth, syncing the mathematical states of tens of thousands of chips using zero sharding, completely bypassing the CPUs.
It's beautiful.
It is a stunningly elegant architecture. But, you know, when you start stacking tens of thousands of anything into a physical warehouse, the sheer reality of the hardware sets in.
The physical world is messy.
Very. Elegant math eventually meets brutal thermodynamics.
It always does.
Yeah.
We are now talking about the chaos of scale. When you deploy 20 or 30,000 GPUs to train a frontier model, and you run them at maximum thermal capacity for 3 or 4 months straight, well, perfection is not just difficult, It is statistically impossible.
The sources outline this harsh reality very clearly, actually.
Yeah.
At a 10,000 plus GPU scale, hardware failures are not anomalies. They are routine, daily occurrences.
Every single day.
You are pushing silicon to its absolute thermal limits. A GPU literally melts down. A power supply trips. An optical transceiver on an InfiniBand cable subtly degrades and starts dropping packets.
And think about the blast radius of that.
Oh, it's terrifying. When thousands of GPUs are running a synchronous all-reduce operation, they all have to finish before the next step can begin.
Every single one.
So if exactly one GPU out of 10,000 fails to respond, the entire multi-million-dollar cluster hangs, everything stops.
The whole thing freezes.
The other 9,999 GPUs just sit there, burning electricity, waiting for a packet that is never going to arrive.
The blast radius of a single failure is the entire training run. The synchrony that makes tensor parallelism and zero sharding possible is also its greatest vulnerability.
So what does this all mean for the engineers? At 10,000 GPUs, a hardware failure isn't a freak accident that ruins your day. It's just a regular Tuesday.
If we connect this to the bigger picture, it means that training a frontier model is a masterclass in robust systems engineering and fault tolerance.
It has to be.
It's as much about surviving hardware decay as it is about advanced AI algorithms.
Which is wild to think about.
The people running these clusters have to design the training loop with the absolute mathematical certainty that hardware will fail repeatedly. So they build incredibly sophisticated, automated checkpointing systems.
I was going to ask about that because you can't just lose 3 weeks of compute every time a cable frays.
No, you'd never finish a model.
Right, but saving terabytes of model state must take forever. Does the whole cluster just pause to hit save?
It used to, actually, but that became way too expensive.
Too much idle time.
Exactly. Yeah. Now they use asynchronous checkpointing. The GPUs copy their state to CPU RAM, and the CPUs slowly write that massive terabyte footprint out to persistent distributed storage, while the GPUs keep crunching the next batch of data in the background.
Oh, that's clever. It's like saving your progress in a massive open-world video game, but doing it seamlessly across thousands of hard drives simultaneously.
That's exactly what it is.
Because when the inevitable happens, when a server rack overheats at 3:00 a.m., the system has to recognize it instantly to prevent total corruption.
The choreography of a failure is fascinating.
Walk me through it. What happens when it breaks?
Okay, so the cluster orchestrator detects a lost heartbeat from a failed node. It instantly pauses the entire 10,000 GPU cluster.
Just a hard stop.
Hard stop. Then it logically fences off the broken hardware so it can't send corrupted data into the network.
Quarantine the bad node.
Exactly. It dynamically reconfigures the InfiniBand routing topologies to bridge the gap left by the dead zone. Then it loads the last asynchronous checkpoint from storage, recalculates the optimizer states, and resumes the training loop.
And it does this automatically.
Completely automatically, in minutes, without losing months of computational progress.
That is insane.
Meanwhile, human engineers are literally walking the hot aisles of the data center, pulling out burnt server blades and slotting in replacements to keep the total compute capacity up.
They're just doing triage in a server farm.
Exactly. It requires 247 human monitoring.
It's incredible. Let's just step back and recap this epic journey of the pre-training pipeline we've just covered.
It's been a ride.
We started with the sheer physical problem of model-sized frontier models are too massive for one chip. That forced us to divide the labor using the math of data parallelism and tensor parallelism.
The chef's in the kitchen.
Right, but that created a multi-terabyte memory bottleneck, which led to the ingenious strategy of zero sharding, slicing up the optimizer states and parameters so no single GPU holds the whole model.
Burning the recipe.
Burning the recipe. But sharding forced the GPUs to constantly communicate, which required bypassing the operating system entirely, using the high-speed nervous system of InfiniBand and RDMA.
Telepathy for silicon.
Yes. And finally, stringing tens of thousands of those chips together brought us to the gritty physical reality of thermodynamics, automated checkpointing, and swapping out burnt GPUs in the middle of the night just to keep the training loop alive.
It is a remarkable, unbroken chain of problem solving.
Yeah.
Every single solution introduces a new, more complex bottleneck, which requires a totally new systems engineering breakthrough.
And according to our technical notes, this concludes the entire pre-training pipeline portion of the sources.
The end of phase 1.
We've taken a massive pile of text data and pushed it through this chaotic hardware symphony to create a base model. But, it's not a useful assistant yet.
Not even close.
Next time, the deep dive will explore what happens after all this massive infrastructure work, fine-tuning, and instruction tuning.
That's where the magic really happens.
It is. That is the magical process of taking this raw, babbling text completion engine that we just spent millions of dollars and megawatts of power training and turning it into a helpful AI assistant that actually understands your questions, maps to human values, and follows specific instructions.
It's where the raw, brute force intelligence is finally shaped into something usable and precise.
I can't wait.
But as we wrap up today's deep dive into the infrastructure, consider the trajectory we are currently on.
Yeah, where is this all going?
Well, we spent this entire time talking about overcoming the limits of silicon and copper. We are building clusters of 100,000 GPUs now, pushing the absolute boundaries of how many electrons we can force through standard networking cables before the heat and latency become insurmountable.
Right, there has to be a physical limit.
It begs the question, how long can we sustain this brute force era? The energy consumption alone is staggering. We might be rapidly approaching the end of the line for traditional silicon architecture.
So what's the alternative?
To reach the next paradigm of intelligence, we might have to fundamentally abandon these copper wire interconnects and shift toward entirely new physics, like optical computing, where data moves via light instead of electricity.
Oh, wow.
Or even neuromorphic biological computing that natively mimics the human brain's insane energy efficiency.
That is a wild thought to end on.
It's the only way forward eventually.
So if you're listening, the next time you type a prompt into a frontier model and the answer appears instantly, remember the sheer scale of the operation making that possible.
It's easy to take for granted.
It really is. Remember the thousands of tiny shards flying across InfiniBand cables, the constant saving and loading, and the symphony of silicon working desperately behind the scenes just before it hits a thermodynamic wall?
It's not magic.
No, it's not magic. It's just incredibly, unfathomably good engineering. Thanks for joining us on this deep dive. Keep coding, keep building, and we'll see you next time.